Now we also need to talk about the TCP flags. And we saw that when we talked about the three-way handshake and the four-step shutdown process. We have a SYN, which is a synchronization flag. It's usually at the beginning of that communication, right? Extending my hand, I want to synchronize with you. Let's establish this communication so we can pass some data back and forth. Hopefully we'll get an acknowledgement. I will try to synchronize with you, and if I get an acknowledgement, I know you're there. I know we can start this communication process. You may see another flag called push, PSH. That means force the data. For whatever reason, we need to push that data across the network. Stop buffering it. It needs to go right now. We have an urgent that specifies the data packet is urgent. So it may get pushed to the front of the line so it can get there quicker. Password changes. Data that is deemed urgent will get there faster. We have the FIN, F-I-N. That's the finish flag. All right, and I'm not talking about the country. I'm talking about the finalize or ending our connection. We're finishing the communication stream we have. And this is you may hear this as a graceful shutdown, right? I synchronized, you acknowledged, I acknowledged your synchronization, we passed some data. Now I'm going to send the FIN flag. Say, hey, I'm all done. We saw that in the four-step shutdown process. And then the reset is kind of like the finish flag, but it's not nice about it, right? It can happen in the middle of the communication. Something could be going wrong, and you can say, wait, stop. We have to reset this connection. So as soon as we reset, then we have to go through this process again. We have to do the synchronization and the acknowledgement and get that communication back up so we can start passing data. So be familiar with those 6 flags there. They're going to be important, especially the SYN, SYNAT, well, all of them, because we can run different attacks with these TCP flags. We need to know how to stop those, right? You may have heard of a half-open attack or a stealth scan. This is what they're talking about, the SYN and SYNAT flags. So here's a TCP header. All right, so talking about that transmission control protocol, this is the first thing that's read from a packet, right? Because header information is at the top. The data is usually below. Header information is up here. What's in the header information? Well, source port, destination port. In a TCP header, we also have, look, the sequence number, acknowledgement number, those flags we just talked about. The window size is in there as well, and we didn't really talk about that one. But the source port and destination port, we did talk about those. Where am I going and where am I coming from? That's important information. What door am I going to try to enter when I get to the destination, when I get to the other end? And what door did I come out of? Because more than likely, you're going to send me some information back. You need to know what door to come back into when it comes back this way. So that information needs to be there. We talked about sequence number and acknowledgement numbers, but the window size, that's how much information we can send between acknowledgements. I can send you some data, send you some data, send you some data. Did you get that? Yes, I did. Cool. Send you some data, send you some data. Did you get that? Yes, I did. Cool. And I can keep doing that, right? That's the window size. How much data can I send at any given time before you're going to say, I'm good, I'm good. And we want to send as much as possible, but sometimes that doesn't happen. Network congestion, latency, routing issues. Sometimes that window is large. Sometimes it kind of shrinks back down and comes back up and shrinks back down. So it can adjust to network conditions, but that's negotiated usually in that three-way handshake. And then here is a UDP, user datagram protocol, that we've not really mentioned much. This is his header. A little bit smaller, don't you think? Now all we have is a source port, destination port pretty much. There's a length and a checksum in there for our CRC, but for all intents and purposes, there's no acknowledgement, there's no window size, there's no sequence numbers. It just needs to know where it's going, where it came from, and it's going to take off. A lot smaller header than TCP, still at layer 4. All right, remember layer 4, TCP and UDP at our transport layer there. It is a connectionless best effort protocol. It's connectionless because it doesn't have that three-way handshake. It says, I have data, I go in that way, and takes off. It's faster, less overhead, but it's not as reliable. And then that internet protocol, just taking a look here at its header, we know that IP protocol provides addressing for packet delivery. It shows us the way, right? Now, don't get that confused with TCP. We know TCP is responsible for the actual delivery. IP addressing just says, hey, you need to go that way to get to your destination. Internet protocol, logical addressing. We need to think about routers and routing when we're talking about IP. Layer 3. Then we also have something called ICMP that you need to be familiar with because you're probably going to use this for testing and trying to see what's out there. You may be the victim of a ping sweep. ICMP is Internet Control Messaging Protocol. This is how we get status information. Have you ever opened up a command prompt or been on a router or a switch and you're trying to reach another device, a distant device, and you may get something like destination cannot be reached? Well, that's ICMP doing its job because it's going out to see if it's there and giving you the error message back. Instead of just going out into oblivion and you don't know if the information got there or not, ICMP gives us those error messages, those status messages. And, I've mentioned ping a couple of times, but traceroute uses ICMP, this protocol as well, to do its job, right? Traceroute is what's showing us the way of how to get from point A to point B, let me back up. It's not really showing us the way, it's showing us the path that it's taking, right? It will show us the hops, the routers. How many routers is it going across to get to the destination? So you could open up a command prompt and type traceRT and the IP address, and it will leave your host, go to your default gateway and go out to the internet. And you'll see, hopefully, the hops or the routers that it's taking to get to the destination. ICMP is responsible for that. Now, here's some types and some codes. You might want to file these away in the back of your head. Echo reply and echo request. Those are the ones that we're most familiar with, right? If I send you a ping and that is an echo request, right? I'm looking for a reply, an echo reply. Because if I ping you, I'm sending something to you. Think of like a submarine, right? If they send out a ping in the water, it will bounce off another piece of steel, another boat or another submarine, and bounce back to me. If I get that signal back, what does that mean? That means somebody is there. Same thing when it comes to computers. I'll send out some electrons, a ping packet, and if I get it returned to me, I know you're there, I know you're listening. That's important because that's going to be the first step a hacker is going to be doing to footprint your network. They're going to use that information and ping that computer and ping that computer and ping that computer. Well, 1 and 2 is up, number 3 is not responding. So I'm not going to attack number 3. I can't reach it. It may be turned off, unplugged, off the network. I can reach 1 and 2 though, so I'm going to perform my attack on them. That's why ICMP is important. We also have something called ARP, Address Resolution Protocol. Now this is layer 2, right? We're moving down the stack if you've noticed. Now we're down there at layer 2, the data link layer. This takes our IP addressing and converts it to a MAC address or a hardware address or Ethernet address. Remember, they're all synonymous. So we develop our applications to use IP addressing, the logical addressing, because it can change from system to system, computer to computer, device to device. But we tell our application, go get the IP address from the TCP/IP protocol stack. Have you ever gone into your network settings on your host before and changed the IP address or looked at the IP address? It gets that information from there. We tell applications go look at there to get our information. Once it gets the IP address, then it needs to get the MAC address, because remember earlier I mentioned information is delivered to a host via layer 2. not layer 3. So we need the MAC address. So what the ARP does, the Address Resolution Protocol, it will say, well, I've got information destined for them. I don't know their MAC address. Because we can't hard code that into every application we create. That's not feasible. But I know the IP address because I pulled it from the TCP stack. So I'm going to send out a broadcast and say, hey, everybody, I have some information destined for 192.168.100.100. Who has that IP address and what is your MAC address? So being a broadcast, everybody is going to get it inside of the broadcast domain on our side of the router, inside our local network probably. If that's not you, you're going to ignore it. But if I'm 100.100, I'm going to be like, hey, that's me. Here's my MAC address. So he will reply with his MAC address. Now the computer that's doing the sending can say, ooh, I got the MAC address now. Take that information and plug it in to where it needs to go. Then it can go ahead and finish encapsulating that data and send it down layer 1, remember, down the physical layer, and send it on. Now, wherever it reaches, let's say it gets to a switch, and we're going to talk about those a little bit later, it's going to look at the destination MAC address and figure out where it goes. Or everybody's going to get that information, look at the destination MAC address, and say, no, that's not mine, discard. I'm going to get it and say, oh, that's my MAC address. That's my information. And I will go ahead and process that and start pulling those layers off, because what do computers care about? Do they care about IP addresses or TCP or UDP? No, they want the data. So I'm going to tear off IP. I'm going to tear off TCP. And I'm going to get up to the data that you've created on the distant end just for me. Now we have quite a few application layer protocols. We're back up to layer 7 now. And I put these in here because I think they're going to be important, especially when it comes to those secure protocols, because that's the way we want to go, right? We have HTTP and HTTPS. Well, the S is the one that is secure, right? That's what we teach everybody, right? Make sure it says HTTPS because the S is for secure, meaning we're using some type of certificate more than likely, like an SSL certificate or a TLS certificate. We know HTTP and HTTPS, that's our web traffic. DNS, domain naming service. All right, this guy's very important, and it's important when it comes to security as well, because somebody could poison, say, our DNS. What DNS does for us, it is our host name or URL resolution to IP address. We as humans, we speak and label computers with names and web addresses with names. But we can very well get to the same web page by typing in the IP address of the distant end server. But it's hard to memorize all those IP addresses, right? We can remember labels really easy. So DNS takes those labels and converts that to an IP address, because routers and switches and layer 3 switches and all those networking devices, they talk IP addresses. They don't talk something.com or .net. They understand numbers. So DNS converts that to numbers for us, and that's how our traffic goes from whatever we type in, some .org, to an IP address and gets to the distant end. SMTP, that is our mail, right? Simple Mail Transport Protocol, port 25. That's how information is sent from server to server or sent to you at the end. POP3, that's our post office boxes that we have, right? A little older technology, but it's still for our email, just like IMAP and IMAP 4 being the newest one out right now, right? So that is for our email delivery as well. SNMP, Simple Network Management Protocol, that's where we can have devices on our network, routers, switches, IDSs, IPSs, and we can stick agents on those devices. SNMP allows us at a terminal or management type computer to manage those devices that have the agents on them. So we can see if interfaces are down or how much traffic is flowing, or if there is a problem, it will let us know. So that helps us manage our networks. FTP, TFTP, and SFTP. Those are all file transfer protocols, right? Now, FTP and TFTP, not secure. Plain text passwords, plain text usernames. Don't use them if you can help it. We want to use SFTP, secure FTP. We don't have our username and passwords passed across the network in plain text, where anybody with a wire sniffer, say very popular on Wireshark, is using. They can see that traffic, they can see that information and simply write it down, record it, and now turn around and use that username and password. Telnet and SSH, all right, remote connections. Telnet's not secure. Again, plain text username and password passed across. SSH, secure shell. Secure, it's in the name, right? It is encrypted. Username and password is not plain text. Then we have SCP, right? Secure Copy Protocol, another alternative to FTP. NTP, Network Time Protocol, another one that's important for us to secure, because if I can manipulate the timing on your network, I may be able to inject information into your network. I may be able to break domain services. And then LDAP, that Lightweight Directory Access Protocol. We can use this to access directory information, which is a plethora of information when it comes to your network infrastructure. I can get usernames, password hashes. I can get contact information, office load, whatever you put in the directory services, right? Most of the time there is username and passwords, but people add all kind of other stuff. Calendar information in there, contact information, addresses, all kinds of stuff can be in directory services. LDAP allows us to get that information out. Then we also have something called NetBIOS, Network Basic Input and Output Systems. Now for network calls, this is used for network calls to remote devices. Now this is kind of an older technology that we not really used as much anymore, but I want you to be familiar with it because it could be a vulnerability. We have session mode and datagram mode. Session mode is connection oriented. Think kind of like TCP. Datagram mode is connectionless, which sounds a lot like what? That's right, UDP, because it's connectionless, it's just best effort, it sends it and forgets it. Now NetBIOS is at the session layer, and that is a layer 5 protocol that we're talking about here. So next, we're going to continue with domain 4 and the network architecture area, starting with multi-layer protocols.